All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. We have made it to the end of Unit 5. That's exciting, right? And so we're going to end by talking about catalysts, how they work, and how they influence reaction energy profiles. Okay, and so I know that you probably have a background, you've probably seen catalysts in the context of biology, and we've certainly seen them in the context of reaction mechanisms, but we haven't really dove into what exactly is going on here. And so that's what this particular section is hopefully going to give us some insight into. So as we end this unit, let's do this, let's knock it out so that we can get ready for our test, because I know that's what everybody's excited about. All right, so catalysts, what are they? A catalyst is a substance that changes the rate of a chemical reaction without itself undergoing a permanent chemical change in the process, right? So when a catalyst gets added, it increases reaction rate, and it doesn't change, right? It's not chemically involved. Its bonds are not being broken or reformed or changed in that process. Now, we need to consider there are two different types of catalysts that we can encounter. You're going to have heterogeneous catalysts, which means that when you think about whatever your reaction is taking place in, it's going to be in a different phase. So consider where you got two gas reactants reacting. Let's say that you have a solid catalyst. That's going to be a heterogeneous catalyst. And you have homogeneous catalysts, are catalysts that are going to be present in the same phase or physical state as the reacting molecules. So in the same example, let's say you had two gases that are reacting, you got a gas catalyst. Or let's say it's aqueous. You got two aqueous solutions, you got an aqueous catalyst, right? Those would be examples of scenarios where it would be homogeneous. Now, let's consider the following example. We got hydrogen peroxide, and we know that it decomposes very slowly in the absence of a catalyst, and it undergoes a very slow decomposition, right? It goes from hydrogen peroxide to liquid water and oxygen gas. Simple, single, elementary step, that's the process. But what we've identified is that, okay, if hydrogen peroxide is placed in the presence of bromide ions, and it's in an acidic environment, that decomposition is going to occur much more rapidly. So the rate of that process, it'll decompose into that water and oxygen much more quickly. Now, in doing so, we get a completely different mechanism, right? So we introduce our acidic environment, we add our bromide ions, we've got our hydrogen peroxide, it goes to bromine and water. Then the bromine reacts with the hydrogen peroxide, we get our bromide ions back, we've got hydrogen ions, and then we've got oxygen, right? And what we see here is that, again, bromide is the homogeneous catalyst here because it gets regenerated at the end of the reaction. Overall, you still have the same net reaction. You get 2H2O2 produces 2H2O and oxygen, right? So even adding a catalyst, you still get the same net reaction. You've just now presented a different reaction mechanism for this process, right? Initially, we had a single one-step process where the hydrogen peroxide loses a bond, loses some oxygens, and you get the formation of oxygen gas and water. Here, we've got this two-step mechanism. All right, so let's dive into how exactly does a catalyst perform its function? So how does it actually increase the reaction rate? Like, we can say it does that, but how? And so in general, what we know is that catalyst will operate by lowering the overall activation energy for a reaction, right? So the total activation energy for the process, whether it's a one-step, two-step process, doesn't matter. The total activation energy is going to be lowered when a catalyst is added. It lowers our energy of our activated complex, or complexes depending on the process. Now, catalysts can also operate by increasing the number of effective collisions that are taking place within this particular chemical process. Because remember, collision theory states you need to have enough energy, you need to have collisions, and you need to have proper orientation. So if our catalyst can increase those three factors by giving more effective collisions, maybe more proper orientation, or maybe it facilitates that lower activation energy, or maybe it just increases the number of collisions. That's going to cause the reaction rate to increase. Now, like we saw on the previous slide, adding a catalyst provides a completely different mechanism for the reaction, right? So we went from that one-step decomposition of hydrogen peroxide to a two-step process, right? So we saw it decomposed without a catalyst, just goes H2O2 directly to water and oxygen. With the catalyst, you got bromine, aqueous bromine that was generated as an intermediate. And so still able to carry out the same process, but it's still overall lower in energy. Now, when a catalyst gets added, we see that, like in this case, we had an intermediate. What we need to see is that overall, and what's going to happen is that the activation energies for both steps are going to be, or should be, or must be lower than the activation energy for the uncatalyzed reaction, right? Because if not, then you've just carried out the same process and it's taking the same amount of time or even longer, and it's supposed to be making the reaction rate faster. So anytime you add a catalyst and an intermediate gets produced, you're going to have at least two steps, and those two steps activation energies will be lower than the one-step activation energy, right? And we can see how that kind of plays out. So if we think about in our process, the red curve represents the uncatalyzed reaction. The blue curve represents the catalyzed reaction. And you can even see here, like if you took the sum of these energies, I think from here and here, and compared it to here, the blue curve would have an overall lower activation energy, right? And what we can see that's going on is that in the uncatalyzed reaction, if you think of the number of collisions that have the appropriate energy, we've got that red section that's shaded in. That's going to correspond to our red curve. But for our blue reaction pathway, it's going to carry what's shaded in blue plus what's shaded in red. So we can see that we've got a significantly greater number of collisions that have the appropriate energy to be able to react. And so that's going to help facilitate the reaction occurring much more quickly, right? So that's the last thing that I really needed to talk about. I'm going to be producing another video that goes into some more details on catalysts, like adsorption and things like that next. But this is like the last piece that you need for the exam and for your test. So hopefully this was insightful. If you have any questions, fill out the Google form. And if not, I'll see you guys in class real soon. Take care.